Hi, my name is Valentina Betancourt, and this is my presentation for Lab 1, Charge Tapes. An introduction to the lab. The purpose was to measure how much excess charge is on an object, in this case, a common household object, a clear piece of tape. The reasoning is that it is difficult to gauge how much excess charge is on a clear piece of tape, and we only have a vague range. So in this experiment, we looked to determine the force exerted by one piece of tape onto another when they're measured a distance apart. We do this since we know ordinary objects acquire an excess positive or negative charge from simple interactions with other objects, such as touching, rubbing, or pulling. We then use this force to determine approximately the amount of charge on one piece of tape. Simplifying assumptions. First, in this lab, we treat a long piece of tape as if it were a point charge with all the charge concentrated on the center, and we assume that each piece of tape has about the same amount of charge. Theoretical principles that are relevant in this lab. First, Coulomb's law, which we use to calculate the electric force between 2 point charges. Then gravitational force, calculated as mass times a gravitational constant. And lastly, Newton's third law, which states that for every action there is an equal and opposite reaction. Initial measurements. The length of one piece of tape that I personally used was 1.981 centimeters, and the mass was 0.1981 grams. Expectations and observations. First, throughout this lab, I observed that two pieces of tape repelled each other since they had the same sign charge. A piece of tape and a book, which was a neutral object of my choosing, attracted each other, and a tape and a pen attracted each other as well. In this case, a negatively charged pen. Therefore, it was safe to state that the tape had a positive charge. The first calculation that I made from these measurements was the magnitude of the gravitational force on tape B, calculated as mass times the gravitational constant. My mass was 1.981 times 10 to the negative 4 kilograms times 9.8 meters per second squared, and arrived at 1.94 times 10 to the negative 3 newtons. The distance when the tape began to float was approximately 0.01 meters. This actually occurred when I put one piece of tape between two books and it started getting closer to it with another piece of charged tape, and the distance in which the top tape looked like it was floating or when they began to repel, this was approximately 0.01 meters. Then I calculated the charge of tape B, setting the force of gravity equal to the electric force, where the force of gravity was mass times the gravitational constant, and the electric force is 1 over 4 pi epsilon naught times q squared over r squared. Plugging in appropriate values and solving for QB, I arrived at 4.644 times 10 to the negative 9 coulombs. Then I calculated the corresponding number of electrons on tape B. I knew that there was 1.602 times 10 to the negative 19 coulombs per electron, and I then multiplied that times the charge of my tape. This helped me arrive at 2.89 times 10 to the negative 10 electrons on my piece of tape. Following a similar process, but using number of atoms, I got 0.1981 meters, the distance, or the actual length of my tape, and divided by 1 times 10 to the negative 10 meters, which is the approximate size of an atom. Dividing this, I got 1.981 times 10 to the 9 atoms on my piece of tape. The ratio of the number of electrons to the number of atoms on the sticky surface of tape, I got these two previous answers and divided one by the other, in this case electrons over atoms, and got that there was 14.589 electrons per atom. Concluding questions. If electrons had a positive charge and protons a negative charge, nothing would actually change about the observations that I made with my tapes and other objects. Two tapes would still repel, a tape and a neutral object would still attract, and tape and a negatively charged pen would still attract. It is also important to state that you have to be very careful when handling the charged tapes, and you should actually handle them as little as possible. This is because the charged tapes lose charge as they come into contact with other objects. Here is a snapshot of my code and the output. On the left-hand side, we can see the two yellow spheres are the actual tapes being treated as point charges, and the output of my code is the electric field for each piece of tape. On the right-hand side, we can see first I set constants and then created objects first for tape A and then also for tape B, and then created a function which would take in a point charge, whether A or B, and a starting location, and then calculate the electric field and the electric force. In the diagram, once again, the blue arrows are the gravitational force on each piece of tape. The red arrows are the electric fields, which are somewhat covered by the white arrows, and the white arrows are the electric force on each sphere, which once again is a point charge modeling the pieces of tape. That concludes my presentation. You can see a more in-depth look at the actual code through the link for GlowScript. Thank you so much.